Hi everyone, welcome to another e-learning day. Today we're going to focus on Chapter 1, Section 2 and just do a very basic introduction to what's called parent functions. So these parent functions are what we refer to as our original graphs, something that it looks like before any types of transformations have occurred to it. Before I do that, though, I'd like to remind you of the transformations we've just discussed in the last e-learning day. So that would be your Chapter 1, Section 1 notes. If you have your note-taking guide, it might be helpful for you to pull that out and use it as you follow along with today's notes and attempt tonight's homework assignment. We discussed 3 different types of transformations. The first was translations. So this is when we were adding a number that could have been inside of the power, so that would be moving it left or right, or outside of the power, which moved it up and down. We also have a reflection, and that's going to occur when the a value is negative. The a value is the number in front of the power. Okay? So when that is negative, we're going to have a reflection, and we're going to stick to just reflecting about the x-axis for now. The rule that we noticed last time was if I have the original point xy, after a reflection, it becomes x comma negative y. The y was opposite. And lastly, we talked about stretches and compressions. This is what actually changed the shape of the graph. So the stretch, remember, the graph would get longer and thinner, and the compression would make it sort of look wider or fatter. A stretch is when a is greater than 1. So this is going to make the function move at a faster rate. And the compression is when that a value is between 0 and 1. So that's going to slow down the rate at which the function's growing, which is why it has that appearance of looking wider, or like I said, fatter. I want you to take a look at this portion of your note-taking guide. These are our parent functions I'd like to start off with. As you can see, we have linear functions, which we've already discussed. Our next unit is going to focus on quadratic functions. This shape is called a parabola. It can open up, it could also open down, but it's always going to have that U shape. A cubic function sort of looks like an elongated S, and a square root function has a starting point, and it extends forever in one direction. So these are our original graphs. We also are going to be taking a look at domain and range. You've seen this before, and you should be familiar with the idea that domain is looking at the x values, range is looking at the y values. You would have used inequalities before, but we're going to do something called interval notation. This is going to get you prepared for pre-calculus. So I'll talk about that a little later on in the notes. I do want to point out for all of these parent functions, they are passing through the origin, which is the point 0, 0, but also they're passing through the point 1, 1. So knowing this will help us graph the parent function in order to compare it to other graphs, so we can easily see the transformation. I'll show you what that looks like in the next few examples here as well. Let's go ahead and hop right into it. For this set of examples here, it says identify the parent function for each graph, then describe which transformation of the parent function it represents. Starting with number 4, I see by the shape of the graph, this is a parabola. So I know if this is a parabola, that means it's going to be a quadratic function. So my parent function is quadratic. Okay. Now I want to identify what the transformation was. So how did it change? This is where I was saying knowing that it passes through the origin and the point 1, 1 in our original or parent function, sketching that out real quick can help us see how it's moved. So when I'm comparing my parent function to my new graph, it appears, if I'm comparing this point to this point, this is called the vertex, it's the minimum of the parabola, it looks like it's moved left 2 units. So I'm going to put left 2. And then I just want to check, are there any other transformations? Because there can be more than one. And no, I don't see anything else. Let's skip to number 5. The first thing we want to do is identify the parent function. Well, this one's easy. It's a line. So if it's a line, it's going to be our linear function. So I'm just going to put linear here. And now I want to write what the transformation is. So I'm just going to quickly sketch my parent function. It's going to look something like this. There's actually multiple answers that you could put here. It just depends how you see it. When I take a look at this, I see it as moving down 3. Okay, so 1, 2, 3. Yep, it looks like it's moving down 3 to me. However, you may notice it could also work if you would say it looks like it's moving right 3. Or some people might even say it's moving right 1 and down 2. Okay, example 6 right here. Looking at the shape of the graph, it appears to me that this would be a cubic function, because it has that sort of elongated S shape. Now, initially when looking at it, you're like, it doesn't look like it's moved up or down, left or right. It's still passing through the origin, so maybe no transformation has occurred. But remember, the parent function actually passes through the origin and the point 1, 1, and for the cubic, it also passes through the point -1, -1. So this is what the parent function should look like. So now I need to determine, okay, well, what type of transformation would cause something to look like this and now look like this? Well, essentially, what's happening here is the function has been flipped. And when a function is flipped around a line, in this case the x-axis, we call that a reflection. You can just write reflection. I'm going to be a bit more specific. It is a reflection about the x-axis. The x-axis is our line of reflection. Okay, now I want to take a look at what's called interval notation. Now, we're going to use this to write what the domain and range would be. Remember, domain is when we take a look at the x values, and range is the y values. When using interval notation, there is a specific way we need to be writing it. So first off, for domain, we always want to read the graph from left to right. And range should always be read down to up. We're starting looking at the bottom of the graph, and then we look up at the top. Interval notation kind of looks like coordinates. A coordinate is this, x comma y. Remember, it's a point on a coordinate plane. And you always use parentheses, and the x value is always here. The y value always must be here. Similar idea, kind of, but not really. For interval notation, we're going to be using brackets and parentheses. Okay? Now, in the first position will be how the graph is behaving to the left of the graph, and the second position will be how it's behaving to the right of the graph, or vice versa, moving from down to up. Now, A bracket means that something, that number or that symbol, is either included in the graph, and the parenthesis would be not included in the graph. The best way I can explain this, though, is if we actually go ahead and start taking a look at problems. So let's jump down to number 1. There's multiple parts here. The first part is to identify the parent function. So this parent function is going to be a quadratic function. I can tell by the shape of the graph. It's a parabola. Okay. Now I need to write what the transformation was. So I want to point out, you need to be careful with your scales. This says 2, 4, 6. So each line represents 2 units. I just say that because if you want to graph your parent function, which passes through the point 0, 0 and 1, 1, it would look something like this. Okay? So what is the transformation? Well, going from here to here, it appears that it has moved right 6 units. All right, now I need to talk about the domain and range. Looking at this parabola, it appears to have a minimum value at the point 6, 0, where 6 is the x value, y value is 0. Now, when I'm writing domain, we want to look at the left side of the graph and then compare it to the right side of the graph. So as this function moves to the left, it's always going to be defined. This parabola is going to keep going and going and going and going and going. So it's going to keep going towards negative infinity, because this way we'd start running into negative numbers. The right side of the graph will go towards positive infinity. So we're going from negative infinity to positive infinity. Now, both of these are really symbols. They're not numbers. Infinity is something we cannot obtain. It's something we cannot reach. So because it is not included, we can't actually reach infinity, I need to use parentheses. If you're going from negative infinity to positive infinity, that means all real numbers are included in this range. So there is a symbol we can use for that. Again, it's all real numbers. It sort of looks like the paragraph symbol, but it's an R instead of a P. Now, range is restricted with a parabola. I have a minimum. Okay? So I always need to read range down to up. The bottom of the graph has a y value of 0. So I'm going to ignore the 6. The 6 is an x value. I didn't use it. I'm using 0 for the bottom of the graph. And it is a point on that graph, so it is included. I need to use a bracket. And as the function goes up, it's going to keep going and going and going. That means it is approaching infinity, which we've already discussed means you need to use a parenthesis. Infinity cannot be reached, so parenthesis goes there.